Hello everyone, in this video we will see the time response analysis of a first order system. What is meant by order of a system? Order of a system means the highest power of s in the denominator polynomial of a closed loop transfer function. So first order means the highest power of s in the denominator polynomial will be 1. So let us consider a transfer function for a first order system, that is c of s by r of s is equal to 1 by ts plus 1. So in this transfer function we can see that the power of s is equal to 1. So this is a first order system. So for getting the time response of the first order system, for any of the system you have to give the input. So input can be any of the standard test signal. So let us consider the response to a unit step input. So we are considering the input to be a unit step. So unit step, we know that r of t is equal to 1. Amplitude should be 1. So when you take the Laplace transform of this, you are getting r of s is equal to 1 by s. Now, you know that transfer function is c of s by r of s, that is equal to 1 by ts plus 1. So when you cross multiply this one, you will be getting, bringing r of s to the other side, you will be getting c of s is equal to 1 by ts plus 1 into r of s. So we know r of s is equal to 1 by s, so you can substitute it here. So we'll be getting it as 1 by ts plus 1 into 1 by s. So here it is 1 by s into tau s plus 1. You are getting like this. So now you know that c of s, we have an expression. Now we have to find the time response for this one. So for time response means we need to get it in time domain, that is we need it to be, the output should be c of t. So for getting that one, we need to take the inverse Laplace transform of this expression, but this expression is not in standard form, so we have to do the partial fraction expansion. So let us take the partial fraction expansion, that is 1 by s into ts plus 1 is equal to a by s plus b by tau s plus 1. So when you do this partial fraction expansion, you will be getting a is equal to 1 and b is equal to minus t. Now substituting in this equation, you will be getting c of s. So I can substitute now c of s, I can just write it as a by s plus b by ts plus 1. So a is 1, so it is 1 by s, minus b is minus t, so minus t upon ts plus 1. So this is what you are getting for c of s. So this I can just rewrite it as 1 by s minus this one as t by, I can just take the t outside, take t outside and put it as s plus 1 by t. Okay, so this t and t gets cancelled, so we'll be getting it as this one becomes 1 by s minus 1 by s plus 1 by t. Now we can easily take the inverse Laplace transform of this one. So c of t is equal to, when you take the inverse Laplace, that is inverse Laplace transform of 1 by s minus 1 by s plus 1 by t. So we have the inverse Laplace transform of 1 by s as 1 and 1 by s plus 1 by t. You know that 1 by s plus a, the inverse Laplace transform of 1 by s plus a is nothing but it is e raised to minus at. So here we have 1 by s plus 1 by t, instead of a we have 1 by t. So here this one is e raised to minus t by t. So this is the response. So this one is for t greater than or equal to 0, because this output for unit step input, we know that the output is present only for t greater than or equal to 0. So here this one is the time response for a unit step input for the first order system. So when you draw the graph, you will be getting something like this. So unit step means we have given 1, this is the step input. So here when you take it, it will be growing like the waveform will be going like this, and this is the time. And here now when t is equal to t, what happens? At t is equal to t, that means we are substituting t is equal to t in this expression. So at t is equal to t, we have c of t is equal to, we can just get it as 0.632 as the answer. So let us consider this one as t, that is capital T. So here it is 0.632. So this one is this t is known as time constant of the system. Time constant. This is known as time constant. Now we can here, what is the error? So error, how will you find it? Error is nothing but it is equal to the output, the input, that is r of t. R of t, we know that it is 1. So r of t minus the output, what you have got here. So that is the response, the desired output minus the actual output. Here see, r of t minus this input minus this one will be getting the error. So r of t, we know that it is unit step, so it is 1 minus c of t, we got it as 1 minus e raised to minus, so 1 minus e raised to minus t by t. T by t or t by tau, you can say. So you'll be getting it as, here this 1 and 1 gets cancelled, you'll be getting e raised to minus t by t. So this is what you are getting. E of t is equal, this is the error. Error expression is e raised to minus t by t. How will you get the steady state error? So steady state error is nothing but, that is ESS is limit limit t tends to infinity. It is limit t tends to infinity, this one. So we'll be getting this error as limit t tends to infinity e raised to t. So this is our steady state error. So e of t, we have the expression as e raised to minus t by tau. So we can put it as this is limit t tends to infinity e raised to minus infinity by t. So we know that e raised to minus infinity is 0. So we'll be getting it as 0 as the answer. So in this particular case, the steady state error is 0. Now when you observe this output, that is this one, 1 minus e raised to minus this expression, if you see, you can see that here the exponential term, it is e raised to minus 1 by t into t. So this minus 1 by t, this is nothing but it is the pole of the transfer function. So if you see this one, the transfer function, we have it as, the transfer function is s into, so here it is 1 by s into, so if I take that t outside, we will be getting it as s plus 1 by t. So this is same, if you multiply it, you will be getting s into ts plus 1. So now what are the poles of this one? So here when I take t out in the numerator, we'll be getting it as, in the denominator you have s into s plus 1 by t. So what are the poles of this one? Poles, we have s is equal to 0 and s is equal to minus 1 by t. So these are the poles of this first order system which we have considered. Now we see that in this response, we have the exponential term to be the pole. So e raised to minus 1 by t, here in this particular case, this e raised to the exponential power is the pole. So now from the response itself, you are getting the, so the pole is like, it is playing an important role in the stability of the system. Why? Because the response is depending upon the poles of the system. So for example, here we have the response as 1 minus e raised to minus t by t. Minus t by t. So let us take one example in which, e raised to minus 2t, and we have two expressions, e raised to minus 4t. So in this case, if you have two poles, that is pole is present at minus 2 and pole is present at minus 4, we know that this term vanishes faster than this one. So the system which is having a response or which is having a term e raised to minus 4t will vanish than system which is having the power e raised to minus 2t. So that means, as you move forward, like here when you draw this diagram, so we have this exponential power, as I said, it represents the poles of the system. So here you have at pole at minus 2 and another system with pole at minus 4. So minus the system which is having the pole at minus 4, that is this one, will get vanished faster than the transient get vanish faster than the system which is having pole at minus 2. That means minus 4. So as you move away from the imaginary axis, the system is becoming more and more stable. So as the pole is becoming more and more negative, means the system stability is increasing. This is how the stability is depending upon this pole location. So this one, the system with minus 2, pole at minus 4 reaches the steady state faster than the system which is having pole at minus 2. Now let us consider the input. Let us consider the unit ramp input for this one. Unit ramp input. So for unit ramp input, we know that R of t is equal to t. So R of t is equal to t is the unit ramp signal. Now when we take the Laplace transform of this, we will be getting R of s is equal to, we get R of s is equal to 1 by s square. So the transfer function we have C of s is equal to, we have it as 1 by ts plus 1 into R of s. So into R of s, that is we can write it as 1 by s square. So when you expand, you can just write it like this, 1 by s square into ts plus, I can just write it as 1 by s square into ts plus 1. So here again we need to find the response of the system. As you know that we need to take the inverse Laplace transform. This is not in the standard form, so you have to do a partial fraction expansion for this expression. Okay, so we will be doing a partial fraction expansion. So we'll be getting it as 1 by s square into ts plus 1 is equal to a by s square plus b by s plus c by tau s plus 1. So when you do the partial fraction expansion, you will be getting a is equal to 1, then b is equal to minus t, and we are getting c as c equal to t square. So I'm not going into detail of this partial fraction expansion. You can find by yourself. A is equal to 1, b is equal to minus t, and c is equal to c is equal to t square. So substitute it back to this one equation. So c of s is equal to a is 1, so 1 by s square plus b by s, that is minus t by s. Now we have c. So c is t square, so t square by ts plus 1. So this is the expression which you are getting here. So this one I can just simplify and write it as 1 by s square, 1 by s square minus t by s. Now from here I can just take one t outside here. So it is t square divided by t I can just take outside, so it is s plus 1 by t. So from here 1 t gets cancelled. So now this is equal to 1 by s square minus t by s plus t by s plus 1 by t. Now we can easily take, now it is in standard form, we can easily take the inverse Laplace transform. So c of t is inverse Laplace transform of the whole thing. So 1 by s square inverse Laplace transform is t. Then t by s inverse Laplace transform is t. And t by s plus 1 by t, you will be getting it as t e raised to minus t by t. So here you will be getting plus t into e raised to minus t by t. So this one again I can just write it as t minus t into 1 minus e raised to minus t by t. So this is for t greater than or equal to 0. See, time constant indicates how fast the system reaches its final value. So as the time constant is smaller, that means smaller the time constant, faster is the system response. Now when you draw this response, you will be getting something like this. You have, this is our input signal, that is r of t is equal to t. So the signal may be something like this, you will be getting, it is constant, okay. So this is our c of t. So here what is the difference? This one is our steady state error, that is ESS. So E of t, the error I can write it as E of t is equal to r of t minus c of t. So r of t, we know it is t, that t minus t, then minus of that one becomes plus t to 1 minus e raised to minus t by minus t by t. So this is the equation. So we'll be getting now here this is equal to t into 1 minus e raised to minus t by t, and this t and t gets cancelled. So our steady state error is nothing but it is limit t tends to infinity e of t. So when t tends to infinity, we know that this particular term e raised to minus t by t becomes 0. So what is remaining is only t. So this is t, this is our steady state error. You can see that there is a difference between the original input and this output, that is constant throughout, that is t. Okay. So now we will see the response of the first order system for a unit impulse input. Unit impulse input. So here we know that for unit impulse input r of s is equal to 1. Now c of s is equal to 1 by is equal to 1 by ts plus 1 into r of s. So r of s is equal to 1 for a unit step unit impulse input. So we'll be getting it as 1 by ts plus 1. So here this one I can just write it as 1 by t. I'm taking it out, so we'll be getting s plus 1 by t. So now here we don't require the partial fraction expansion because this is already in the standard form, so you can easily take the inverse Laplace transform. So you can find c of t, that is the inverse Laplace transform of this. So 1 by t is the constant, then 1 by s plus 1 by t, that is of the form 1 by s plus a. So that is the inverse Laplace transform is e raised to minus t by t. So this is the response for t greater than or equal to 0. Okay, so now we have this impulse, this response will be somewhat like this. You will be getting something like this. So here this is c of t, and this one is 1 by t, and here it is, this is t. So this is the response for the impulse input. So we have seen the time response for the first order system to a unit step input, unit ramp input, and a unit impulse input. So this is how you can find the time response for any standard input which is for a given input. That can be any of the standard inputs which you can give. So for the first order system, you got the time response, and we found the steady state error also. So hope you understood. Thanks for watching.